Good day, everyone. My name is Najwan Osman Ali, and I am honored to be presenting my paper titled An Adaptive Average Grasshopper Optimization Algorithm for Solving Numerical Optimization Problems at this conference. I am a PhD student at University of Science Malaysia, and my research interest includes optimization algorithm and machine vision. In this paper, I will be discussing the development of a new optimization algorithm that is capable of solving numerical optimization problems more efficiently than the existing GOA algorithm. I hope that my presentation will be informative and engaging, and I look forward to sharing my research with you all today. So let's start with some overview. So I'm going to present adaptive average grasshopper automation algorithm, or the short name is AAGOA. Now, just as an overview, it is an algorithm that is used to improve the original grasshopper automation algorithm, and it is limited for a single objective optimization process. Now, the reason why I'm proposing this improvement is because for a basic GOA, it exhibits some shortcomings, especially in terms of the exploration and the exploitation process, where in this case, the exploration and exploitation is unbalanced, and also it leads to what we call as a slow convergence. And also it has a tendency to fall into a local optimum trap. So these three are the problem statements for the proposed AAGOA algorithm. Now the third thing is the methodology. So for this presentation, I'm going to explain to you how or what are the proposed method that we are going to modify in the original GOA. So there are two proposed modification. The first one is that we're going to modify the parameter convergence value that controls the balance of the exploration of the original GOA. And also we are going to implement a method called adaptive average for target fitness. So we are going to go more deeper in our next slides. So this is just an overview. So the outline for my presentation is the first, we are going to look at some introduction to GOA, just to give some overview, some brief understanding what are the basics of GOA and how it actually works. And then we are going to look at the proposed algorithm, which is called the AAGOA. And then we are going to look at some benchmark functions where we use the benchmark function to test the performance of the proposed algorithm. And the fourth one, we are going to look at the result and discussion. We are going to see how it compares with the original GOA. And the last one would be the summary. So I'm going to summarize the results that we have obtained using the benchmark functions. So just a little bit about Grasshopper Optimization Algorithm, or GOA. So it has been introduced by Sarami et al. In 2017. Now the basic idea of GOA is that it mimics the behavior of a grasshopper, or in this case a grasshopper swarms in the nature itself. So it mimics how the grasshopper move in a swarm, and based on this movement we can actually, or the researcher produce an algorithm called GOA. Now during the introduction or during the publication of this paper, the GOA is used for single objective optimizations. The basic idea behind GOA is we call it as the social interaction of the grasshopper itself, means that how does the grasshopper behave when it is within a certain distance with another grasshopper. This is what we call as a social interaction. Now the idea inside the GOA is that we will need to identify three zones. So we need to identify what we call as a comfort zone. So this is what we call as a comfort zone. and we also need to have a repulsion zone and also attraction zones. So this three zone is very important because it's going to dictate the movement of the grasshopper. So when a grasshopper is within a repulsion zone, means that it's going to move away from the grasshopper. Okay, let's say we have grasshopper A, here we have a grasshopper A, and let's say the second grasshopper is within the repulsion force. Okay, within the repulsion zone, sorry, meaning that it's going to have what we call as a repulsion force. It's going to move away from the grasshopper C. Now what about grasshopper B? Now for grasshopper B, it is within what we call as an attraction zone, means that the grasshopper is attracted to each other. And then we have the third one, means it's comfort zone. At during this zone, okay, the grasshopper is not going to move, it's just going to be static. Now this can be represented by this graph. It is taken directly from the original paper, and here we can see there's a distance. Okay, the negative value indicates a repulsion force, right? The 0 indicates comfort zone, and here we see a positive value. Now the positive value actually uh, represents the attraction zones. So we have the repulsion zones, we have the comfort zone, and also we have the attraction zone. So this is the basic concept for GOA, and this is, we also still maintain the social interaction for our proposed AAGOA. Now the social interaction can be represented by an equation. So this is the equation where we can use this, we can iterate a few times to get the position of our current grasshopper, of our eighth grasshopper. So here we can see that xi actually represents the position of the eighth grasshopper, right? And then we also have what we call the current position for the eighth and jth grasshopper, meaning here the xi contains the position throughout the dimension, because when we're talking about the position, usually we have 2 dimension, 3 dimension, and it can goes up to more than 10 dimension depending on what kind of application that we use. So here xi and xj, the small letter xi and xj, is actually the current position for the eth and jth grasshopper for the current dimensions, right? So SI represents for all dimension, the small letter xi and xj represents the position for that particular dimensions. And also here we have T. T is actually denotes the best solution that we have found so far. So we are going to also use the current position that we have found to be the best, and then we are going to use that as a reference in order for us to find the position of our eighth grasshopper. And how do we calculate the distance? Because the distance will be the main important criteria that we need to calculate. We can calculate by just subtracting the xj divided by the subtract xj with xid. And then here we have another variable called c. C is actually a monetary decreasing coefficient. Now we use c, which is a very important variable here. The c is used to actually control how the algorithm converges to a solution, how fast the algorithm can converge to a solution. So it is a monotonically decreasing coefficient, meaning that it is a linear variable. The value for C changes from with increased iteration, but in a linear way. And here we have variable S actually represent the strength of social forces between two grasshopper. We have talked about the social interaction between the grasshopper. So S actually represent how strong the social interaction is, how strong the we have what we call how strong it attracts, okay, so and how strong it repulses the other grasshopper. So this is the main equation that we use for GOA, and we also apply this equation, of course, with some modification for our proposed algorithm. Now again, still the original GOA equation, the C that we have discussed before actually can be calculated using this equation where we have our Cmax and Cmin value. Eta is actually our current iteration and L is the total iteration. And here we have what we call as a f value. Okay, so f value, we have f value here that there is what we call as a attraction intensity. So f is the attraction intensity, and usually we just use the default value given by the researcher, and L is the attraction length. Again, we are using the default value given by the researcher. So let's move on to the proposed algorithm, which is adaptive average grasshopper optimization algorithm, or AAGOA. Now for AAGOA, we are looking at the original equation for the GOA. So the modification that we have done for AAGOA is that we are proposing a modification in terms of this part, which is the convergence parameter, and also the target position value. So these are the two things that we are going to improve. We are still using the main equation for GOA, but we are going to improve in terms of how we can increase the convergence rate of the GOA, and also we can further improve how fast it can convergence to a solution by changing the target position value. So these are the two things that we are going to do, or we are going to modify in the original GOA. So using the equation that we have modified, so the C in the previous GOA now becomes Cm, and the T from the original GOA becomes P. So we are going to look at the first improvement, where we modified the parameter convergence value. We change from a linear method to a non-linear method. So how do we change a linear method to a non-linear method? We can just simply change the value, or we can determine the value of C based on certain percentage of the iteration. Meaning, let's say we have 100 iteration, right? 100 iteration. So around 0 to 0.6, 0 to 0.6 of our total iteration, we are going to set the value equals to alpha. Okay, alpha can be calculated by using this equation, whereby alpha is exponential negative 0.5 eta divided by L divided by sigma square, right? And otherwise, the value should be 0.1 if the alpha is larger than 0.1. Meaning that based on this equation, we are going to set the value of alpha if the number of iterations starting from the beginning, which is 0, until 0.6 of our total iteration. And then the value becomes 0.1 within 0.6 of the total iteration until 0.9 of our total iteration. And then at the end of our iteration value, we are going to set at 0.0.5. Now, why do we use this kind of value? If you can see here, when we use a convergence value, the convergence value actually helps the algorithm to explore the search space, right? So we have a search space. So when it is linear, in certain point, the algorithm needs sometimes or a lot of times to do search in order to find the solution. So if it is a linear form, you might miss some opportunity to get the best solution. So in the next slide, we're going to see a graph that shows the difference between the linear and non-linear methods. So we can see here, these are the reason why we use the proposed value for C. Now here for GOA, it is a very linear methods, and for AGOA, we can see it is non-linear methods. Now you can see that in the beginning, it closely resembles to the original GOA, meaning that we can just go straight, try to find the solution in the beginning, but when it goes in the middles, we want the algorithm to have some times to find the solution. So that's why we can see here the C value actually slightly below compared with the value of the linear method. So here it gives the algorithm some time to search any solution that might produce a better solution, and usually at the end of our iteration, the algorithm actually found a potential value that it can converge. So that's why we can just straightly produce a smaller C value so that it can focus, refine, retune to get a better solution at the end of the iteration. So this is the main reason why we provide or why we propose to have a nonlinear C value. So C again is what we call as a parameter convergence value that helps our algorithm to converge to a solution better. The GOA is using a linear methods. We are proposing to use a nonlinear methods. So the next improvement that we are proposing is that we are proposing, instead of using only the T value or the best solution found so far, another way that we can do is that we can use what we call as a prediction. So here, this is just an examples. We have some previous examples of T. So all this is the position of the grasshopper that has the best position value, meaning we recorded all the T that we have starting from the beginning, the best solution position of the grasshopper, we record, and for each iteration, if let's say any changes to the value of T, we are going to put it inside our database, and then based on the value that we have for T, right, we are going to calculate based on average value. So here, the P is the current position, of the grasshopper with the best fitness value. What we do is that we're going to add with A. So A here is actually this equation where we take the value for T, we subtract with the average value of T for a certain number of window size. Okay, let's say an example, we want to our algorithm to take, let's say, the previous 10 value of T. The previous 10 value of T, calculate for the average, subtract with the original or the current T value. And from there, we can calculate what we call as the vector value or the unit vector. So A is actually a unit vector that we can use to add to the original T. So here we have T. So again, the TW is actually a summation, okay, or the average value of the previous, or the average value of a window size that we have selected. If let's say we selected a window size of 10, we can just select the previous 10 and calculate the average value. We take the average value, we take the current T value, we subtract, and then we calculate for the vector. And then by using that vector, which is A, we can just add to T. Now this is something like a prediction, whereby instead of just using T, we actually predicts the next position or next best position. So it can actually helps our algorithm to move faster towards a convergence value by using this method. Now, how do we implement all these proposed improvement number 1 and proposed improvement number 2? For CM, we are still going to maintain CM. So CM, there's no changes using CM, which is our parameter convergence value. But when we want to use T and P, instead of using 100% of P value, based on the trial and error that we have done, it is best that we use P value using probability. Meaning that we are going to set in our algorithm 0.1 probability of implementing P. Otherwise, other than that, we are going to use T. So meaning that if let's say when we run our program, when we want to calculate for SI, we are going to calculate for probability first. So there's a 10% chance of using P instead of T. Now by doing this, we can actually create a better results instead of 100% using P, because P is still something like a prediction. So we need to mix with the T value, which is the best position with the best fitness value, right, with the prediction of best position for the grasshopper that has the potential to have the lowest or the best fitness value. So we are going to use probability, which is in this case, we are proposing to use 0.1 probability to implement the equation with P. So this equation. So we're going to implement this equation, but before that, we are going to calculate for the probability. 0.1 probability to use this equation, otherwise we're going to use this equation. Now, once we have implemented this method, we need to identify or we need to analyze the performance of our algorithm. One way that we can do is that we can use what we call as a benchmark function. So we are going to use benchmark function using CEC 2021. So you can see or you can refer the reference here at the below. Now for CEC 2021, it consists of unimodal functions, basic function, hybrid function, and also composition functions. And additional things that has been added inside CEC is that it also contains what we call a transformation operator, meaning that each of the types function that we have, it consists of bias, shift, and rotation that we can actually control. So the total function is not 10 functions that we're going to test, but actually there's a 50 functions that we can test based on how we arrange bias, shift, and rotation. Some function consists of bias and shift. The other function might be consists only of bias, and the other might be consists only of shift and rotation. So this is covered inside the paper. Now, based on all the results that we have, we need to do some analysis. So the analysis that we are using, there are two analyses that we have used. The first one is called a fragment ranking test. Okay, fragment ranking test. So based on fragment ranking test, it ranks in terms of how the algorithm actually fare between each other. So here we have AAGOA and GOA, and of course rank 1 is the better algorithm compared to the second one. So mostly we just add up in terms of operator 00 until 111. So these are the operator that we have discussed earlier, and based on this, we just sum everything, and based on the lowest value would be rank number 1, and here we have our proposed algorithm AAGA have the lowest value, so it ranked as number 1, indicating that based on fragment ranking test, the proposed algorithm is much better compared with the original GOA. So the second analysis to help support our fragment ranking test is the Wilkinson sign rank test. Now, using the Wilkinson sign rank test, we can identify whether the changes or the improvement is significant. So here we can see that the positive value means that our proposed algorithm producing significant improvement compared to GOA. If equals means there's no significant improvement, there's changes, but the improvement is not that significant. And of course, the minus indicating that GOA is significantly better than AAGOA. Now we can see that from all the functions that we have, yes, there's a 29 functions that there's no significant changes, but here we can clearly see there's a 19 significant changes that can be achieved using the proposed algorithm compared to GOA. So it is clearly see from the results that we have from the fragment ranking test and the Wilkinson ranking test that the proposed algorithm statistically producing better value compared to the original GOA. So as a summary, the modified GOA, or in this case our algorithm called the AAGOA, that optimize a problem using nonlinear parameter convergence and adaptive average for target fitness, produce better results compared to GOA. And for a future research aims, we want to implement the modification to other GOA variants, hoping that by implementing this method, it can actually further increase the performance of the other GOA variants. So that's it for my presentation. If you have any question, please contact me through my emails. I will gladly happy to answer any question that you might ask. Thank you so much for listening.